previous lecture, we have started our discussion in a new topic of the course, that is the Unit 3, on the topic of convex sets and convex functions. In particular, we have described in the previous lecture the notion of convex set. Then we have got to know a few commonly occurring convex sets, and afterwards a few convexity preserving results were also talked. Now in this lecture we will get to know a very important result in optimization theory, that is the separation result. It neatly states that if we are given a closed convex set and a point outside this closed convex set, then there is a plane that separates out this particular point and this closed convex set. And you know, the entire optimization theory uses some kind of separation result, some kind of one-sidedness. If you want to find descent direction of a function of several variables, then you will find that in one side of a particular plane all the descent directions are lying. So whatsoever optimization theory you wanted to derive, optimization theory entirely lies on some sort of separation results. In this lecture, we will neatly describe the separation result. There are two agendas of this lecture. At first, we will get to know the projection theorem, and then using the projection theorem, we will get to know how to find a separating hyperplane that separates a point and a closed convex set. The entire separation result is depending on the following geometrical fact. The separation result of disjoint convex sets are depending on the following geometrical fact. The geometrical fact is the following. Let's suppose I have a closed convex set. I have a closed convex set S, that is this abstract set. Let me consider this is my closed convex set S, and there is an element Y which is known to be outside the set S. Here S is a closed convex set, the set which is closed as well as convex, and obviously we are considering here the set S is non-empty. We are considering a non-empty closed convex set, and we take a point Y outside the set S. Then all the separation results, they depend on the following geometrical fact, that if we try to take all the distances from Y to the points on S, that means you consider this function f of x given by this distance between x and y, and the geometrical fact says that there exists a unique x bar belonging to S such that fx bar is the minimum most value of all these distances. And here geometrically we note that from Y you take distances from all the elements in S and you get a minimum distance, and this minimum distance is characterized by the following important fact, that wherever you get the minimum distance at the point, let's suppose at x bar you have the minimum distance, then this x bar not only a unique point but also characterized by the geometrical fact that the angle between this vector x to y, this direction, and any direction you take for any x in S, and accordingly you consider this vector emanated from x bar and towards x, this vector and this vector, for every x you pick up from S, they do have angle that is not lesser than 90 degree, and therefore they are making only obtuse angle. You pick up any other x over here and you consider this angle and angle between this x minus x bar and y minus x bar, you get an obtuse angle. And why this is so? This is due to the following fact. This is very easy to observe. Here you note that if we try to find the level sets of this function fx, the level set of the function fx are given by the following sets. Here you note that y minus x equals to a constant. If you take, let's suppose alpha, that gives us a circle centering at y, because x is variable here, right? So y minus x equals to alpha, y minus x norm of it is equals to alpha, gives us a circle. So let's suppose for a small alpha you have this circle centering at y, and this is the circle for a small alpha. Then for bigger alpha you will have another circle, for another bigger alpha you will have another bigger circle, and ultimately you note that when you have the minimum distance from y to x, y to the set S, then in that case this circle will obviously be touching the boundary of the set S, and hence at the extremum situation you have a common tangent between the level set of the function fx and the set S. And if this is a common tangent, this red line is a common tangent, then obviously we note that the entire set S is on one side of this common tangent and y is in another side of the common tangent. Is not that? And if the entire set S is on the common on one side, on different side of the common tangent than y, then obviously whatsoever x you consider in the set S, the angle between x minus x bar obviously is more than 90 degree. Is not that? Here, because once you are considering the distance, and that obviously the distance from y to the set S, and therefore the minimum distance will be given by a perpendicular distance, and therefore this will be perpendicular to this common tangent x minus y bar, and obviously then angle between any x and angle between for any x in S, the angle between x minus x bar and y minus x bar is more than 90 degree. And here we note that you have not only this fact that you have one x bar, but also the fact that this x bar is unique in nature, and provided the set S is a closed and convex set. Now the entire theorems of alternatives or the separations of disjoint convex sets, all the results towards this separation of disjoint convex sets are depending on this simple geometrical fact. Let me just write out the closest point theorem or the projection theorem, although we shall not prove this result because this result needs a rigorous and tedious construction. And if anyone is interested, I will refer one book, the precise page number I will mention, so that any interested student can be referring to that reference. The theorem is the projection theorem or the closest point theorem. Closest point theorem. Closest point theorem, or it is also called projection theorem because this result characterize projection of y to a given set. Here this point x bar is called the projection of y on the set S, and to be more precise, the projection of a given set, projection of a given set, projection of an element on a given set is defined by the following function: projection of a given element y on a set, on a non-empty set in the n-dimensional Euclidean space is denoted by is denoted by p of y on x is equal to the infimum distance from y to all the elements x's in capital X. Infimum and supremum, refer to any real analysis book. Anyway, so now as this result, closest point theorem characterizes the projection of the projection of an element y outside the set S. Therefore, it is also called the projection theorem. The statement of the theorem is as follows. Here we let S be a non-empty, be a non-empty closed convex set, non-empty closed convex set, and y is outside the set S. Then there exists then there exists a unique x bar in the set S such that the point x bar is the minimizing element of the distances from y to the elements in S. And not only that, further the element further x bar is a minimizing element. By minimizing element we mean minimizing this distance element if and only if the angle between y minus x bar and x minus x bar is not lesser than 90 degree for any x in the set S. Fine. For proof, I am not going to prove the result. However, it is interesting to look at the proof, the construction. If any of you is interested, then please refer to the page number 50 of the Bazara, Serali and Setti's book. This is one of the book that I have referred. The title of the book is Nonlinear Programming. And also you can look the same page number 50 of Sun and One's book. Now there are a few immediate consequences. Those are to be noted from this result. The first note is that this result is not necessarily true for a non-convex set. For instance, let me consider one example. Let me just write out neatly that the result is not necessarily true for non-convex sets, and therefore I need to provide one counter example. The counter example is the following. Let me give you one of the examples. You can quickly construct a non-convex set geometrically. However, in a mathematics course, it is always suggested that your writing should be mathematically precise. Your statement should go with mathematical expression. And unless it is not mathematically precise, mathematics course does not have any meaning. And therefore, I need to mention here what could be a mathematical example. For instance, I consider the following example. Let me consider in the R2 plane, I consider the circular arc of the unit circle below the x1 axis. Fine, I consider this circular arc. This circular arc, if we consider, then this set is a non-convex set. To be precise, let me write the set S by this mathematical expression x1 x2 belonging to R2 such that x2 is given by negative of
the square root 1 minus x1 square, and x1 is in between minus 1 to 1. Fine. This is my this below circular arc, and I consider an element y outside S. I consider the origin. Fine. This is my element. This is my element y. Y is the origin of the R2 plane, and here you note that the minimizing distance from y, the minimizing distance of the set is not only one point. There are all the points, in fact all the points in the set S, all the points, whatsoever point you consider, all are minimizing, and therefore the result that I have mentioned just now, the projection theorem, is not valid for a non-convex set. Fine. Also, the result is not necessarily true for an open set. Fine. Now, towards this, you can quickly find out one example. To be mathematically precise, to write the example, don't just write that this is my open set. Don't just draw a figure like this, that this is my figure, this is my open set, and I take a point over here, and obviously the minimizing distance is not belonging to the set. Please don't answer your question in this manner. This is not mathematical answer. Why don't you consider then, if you are drawing a figure like this, why don't you give a precise expression of this figure, so that your knowledge on mathematics, your perception on mathematics will be very neat. Fine. Your presentation will be mathematically neat, and therefore you please construct one set which is an open set, and take an element outside of the set, and find that the result is not true for an open convex set. The result is also not true for open convex set. Fine. Let me also put out that non-empty open convex set. Fine. You just construct one example. I am just giving this as home task. This is very little example you can consider to construct. Now let me move ahead to find the important corollary from this result. The corollary is, although I have detailed, but let me mathematically detail it. The immediate corollary to the result is the following. The first corollary says that the set that we have considered, let's suppose I have a closed convex set. My abstract set is this set. Fine. A general abstract set is this set, let's suppose S, and I have the element y outside of the set. Then the corollary is the following, that there is a hyperplane there is a hyperplane that separate out the element y and the intercept S. That means there exists a hyperplane P transpose X is equal to alpha, where P is a non-null vector in Rn and alpha is a scalar element. Alpha is a real number. So the corollary that I am going to mention is the following, that if y is an element outside a closed convex, non-empty closed convex set S, then there is a hyperplane that separate out the element y and the entire set S. By separate outs, I mean in one side of the hyperplane the entire set S lies, in another side the element y lies. Fine. Now let me just prove it, although this is geometrically vivid to us, but let me just prove it. The result to be neat mentions the following: let S be a non-empty closed convex set, and set in Rn. In our course, we are considering only the vector space n-dimensional Euclidean space. We are not considering any general vector space. So any discussion, if I am not mentioning the set is a subset of Rn, you please consider that the set that I am considering, if I am missing out to mention that it is a subset of Rn, you please consider the set S is a subset of Rn. because our playground is the entire n-dimensional Euclidean space. No general vector space I am considering in this optimization course. Anyway, the set S is considered to be a non-empty closed convex set Rn, and we consider there is an element, one element y, which is outside the set S. Then there exists, then there exists a non-null vector p in Rn, and a scalar alpha such that in one side of p transpose x equal to alpha you have y lying, and in another side the entire set capital S is lying. P transpose x less than equals to alpha for all x belonging to S. Let us now try to prove this result. This result is an immediate consequence of the result, projection theorem result, or the closest point theorem. Let me just prove this result. The proof goes in the following manner. We note that from the projection theorem, there exists a unique x bar inside the set S such that y minus x bar transpose x minus x bar is less than equal to 0 for all x belonging to S. That we have seen. And obviously we note that how to find this vector p. Here we note that the vector p we can consider, why not we consider this hyperplane, although we have several other hyperplanes. This is also one hyperplane, this is also one hyperplanes that separate out y and s. Now here trivial choice of the hyperplane that separate out y and s is this common tangent, this red line. And once this is a common tangent, then obviously y minus x bar is perpendicular to this hyperplane. Is not that? And therefore why not we consider p as, so here we let, why not we consider p as the vector y minus x bar, because this is known to be perpendicular to the common tangent, and this will give us this p transpose x equals to alpha. Let us see. So here p equals to y minus x bar we consider, and obviously then this vector is a non-null vector. This is due to the fact that x bar is an element in S and y is not in the set S. Fine. Let p is this element, then this inequality gives us, p transpose x is less than equals to p transpose x bar. Now if we choose p transpose x bar is equal to alpha, obviously alpha is a scalar, and this is going to happen for every x belonging to S. Fine. And not only this, we also have to prove that p transpose y is bigger than alpha. Now how do we prove it? We note that p transpose y minus alpha is equal to p transpose y minus, expression of alpha is p transpose x bar, p transpose this is equals to p transpose y minus x bar, but p transpose is eventually y minus x bar, and therefore this is the norm y minus x bar square. This norm is obviously norm of p square, as p is non-zero, non-null, therefore this is greater than 0, and this proves that p transpose y is greater than alpha, and hence the result is followed. Fine.
Now I stop the lecture here. In the next lecture, with the help of this corollary and the separation result that we have gone through in this lecture, we will prove two particular theorem of alternatives. Those are called Farkas lemma and Gordon's theorem. This Farkas lemma and Gordon's theorem are referred as theorems of alternatives because they neatly inform that exactly one of the systems out of two linear systems is having a solution. With this agenda for the next lecture, I stop the lecture here. Thank you all for all of your kind attention.